Okay, friends, welcome back. Don't bother drawing the structure of this horrific molecule. Yeah. The overlapping bonds here just are an attempt to generate this complicated three-dimensional structure on a page. I just drew it for fun because I knew it would freak you out just a little bit. Um, this molecule is not on the exam. And speaking of the exam, um, it's in the testing center today, Thursday, and Friday. Pay attention to summer hours, which are different than normal. There are 34 separate items, but they come in groups. So, for example, assigning R and S is a few of them, and so it's not really a 34 question test. It's less than that. 200 points. The point values vary, so you shouldn't really spend a whole lot of time worrying about that, trying to game the system, but each question will list its point value. Let's see. Anything else I want to say about that? No. Any other questions you want to ask about it? Go ahead.
Is it multiple choice like the last one?
It's multiple choice like the last one, yeah. Yes?
No TA interviews for this, correct?
Have they not scheduled one?
Alex said she won't because the test is over today, so.
Oh, well, okay.
I'm sure recitation will be.
Okay. So the reason I don't personally do an exam review is because in the past, mostly it was frustrating for the students because they would ask questions about what's on the exam and I would be evasive. So I decided to save everybody time by doing that. But if you're able to do the kinds of problems on the practice exam, the key thing is that you recognize your misconceptions and mistakes ahead of time. So I think on the first exam there was E and Z issues, right? And if you had a particular misconception about how to assign E or Z, you might get all of the answers exactly wrong. Or you might get some of them right on accident. And fixing that is going to be useful because we use the same rules for R and S, okay? And practicing on those difficult enantiomers versus diastereomers, is it chiral or is it not? I mean, that kind of thing is... so figure out what your specific weaknesses are and then make sure you address them. Now, somebody requested that we look at an optical rotation problem. These aren't necessarily the biggest deal, but I will show you how to deal with it. This is a chiral molecule. It's an anti-cancer drug. You wouldn't ever make this on purpose. Or rather, there's two routes to drug discovery, really, in our world. You can isolate compounds from nature and then see if they have anti-cancer, antimicrobial activity, or you can just go in blind with your own design and throw a bunch of things at it and see what sticks in terms of what is a good molecule for a particular application. This is almost certainly too complicated for somebody to have woken up one morning and said, hey, I want to make that. This was likely isolated from some natural product, and then they discovered it had anti-cancer activity. At that point, they would have either... and I don't know what the source for this one, but your strategy at that point is either to start isolating it in large quantities from natural sources, or you got to figure out how to synthesize it. So I don't totally know what the story is on this one, but it's pretty complicated. But it gets worse. There are other larger molecules that have drug-like properties. Anyway, its optical rotation is plus 41. Remember, chiral molecules rotate plane polarized light because physics. And we'll just leave it at that. However, the extent of rotation, the extent of optical rotation follows a Beer's law basic relationship. I don't know if you guys ever learned about absorbance for something, how it's like an extinction coefficient times path length times concentration. That's not important, but the idea is that the extent of optical rotation depends on how concentrated your sample is, what the path length of the sample is, and then on some intrinsic property of the sample. And it's additive, and we said that opposite enantiomers rotate light in equal magnitude but opposite directions. So we might call this the plus enantiomer of trabectedin because it rotates light in the plus direction. The other enantiomer, which is probably not available in nature, but if you made it, if you synthesized it, presumably you could make it, would have equal but opposite in sign optical rotation. And if you had a 50-50 mixture of both, the one-to-one mixture of both of these would have an observed optical rotation of 0 because the 50% of the mixture that rotates in this direction will be canceled out by the other 50% of the mixture that rotates in that direction. So we're going to define a term called percent enantiomeric excess, and that's going to equal the percent of the major enantiomer minus the percent of the minor enantiomer. And how do you know which one's major versus minor? Well, you look at the sign of the optical rotation. So, for example, if I observed that we had plus 10.5 degrees in a mixture, the optical rotation of a mixture, we would conclude that the major enantiomer is the plus trabectedin and the minor enantiomer is the minus one, simply by looking at the sign and seeing which one adds up, okay, or which one it matches. It's as simple as that. So often we don't know what the composition of the solution is, so it turns out that enantiomeric excess is also equal to the optical rotation of the mixture divided by the optical rotation of the pure major enantiomer. So in our case, it's 10.5 divided by 41.5, and now I have to get out my calculator because I can't do that in the old noggin. Divided by 41.5. It's basically 25.3% enantiomeric excess. Oh, I can't actually spell that out, so I'm just going to go percent EE. Now, percent EE is different from how much percent is one enantiomer and how much percent is the other. Because remember, we defined enantiomeric excess is the difference in the composition between the two enantiomers. So the way to solve this, if we let we'll let X be the major enantiomer and Y the percent of the minor enantiomer, we know that 25.3% equals X minus Y. And we also know, just by the definition of percentages, that X plus Y has to equal 100. And at that point, we can solve it. Now, if you don't like to solve simultaneous equations, the other strategy is to say, okay, I have 25.3% of the plus enantiomer, and then the remaining 74.7% is a one-to-one mixture of the plus and the minus enantiomer. Whoa. Okay, so all I would have to do at this point is divide 74.7 by 2, and I would get 37.35. There's no, don't worry about significant figures, goodness. Of the plus enantiomer and 37.35 of the minus enantiomer. So the total amount of the plus enantiomer is the sum of those two numbers, which is 62.7%, and we'll call this 37.3-ish. Okay? See how we sort of did that? That's really all there is to it. if that's not making sense to you, look up a couple of problems in the book in the section on an antiomeric excess, but it's really no more complicated than that. Anything you want to ask about that? Okay. You overwhelmed? A bit? Sort of worried about the future? I'm sorry. It's going to be okay. Let's see. So I don't know if it's, when you get older, you forget who you've told your stories to. So if I've told you guys this before, forgive me. I think I haven't. I took this class 351 in the fall of 2001. I was newly back from my mission, and I was dating Amber, who I'm now married to. And as time went on, I used to spend like every day and study till like 9 or 9:30. I'm kind of I'm not a night owl, so I'm sure zero of you, I would go to bed by like 10 or 10:30. I have no such constraints on my schedule now. But in any case, I would study till like 9:30. I'd run over down, I forget the name of the street, to Amber's apartment. She was living at King Henry, which was pretty nice. I was living at Sparks 2, which in the early 2000s was a dump. I don't know if it's still a dump, but in any case, I would run over there and see her for like 5 minutes, and I'd run home and go to bed. And at one point, we were driving around talking, and she was feeling like I was spending too much time with the OChem textbook and not enough time with her. And she said, "Don't you want to spend more time with me?" And I was kind of shocked, and I thought, are we breaking up? And I said, well, on Wednesdays I could, which was not the right answer, as you can imagine. But over the years, I used to spend so much time studying, and more than I needed to because of various issues. And in any case, over the years, I got to the point where, and getting married and having kids will do this to you, where you study with the time you have and then you move on to other things. So I am sorry. When I meet students out in the community, sometimes their significant others are with them, and I always apologize to the significant other for the challenges that I'm causing in their relationships. So I'm sorry if that's you. But I've been there, and it does get better. So hang in there. And probably don't take 352 in a spring or a summer term, right? I don't know. Have you learned your lesson yet? Too late? Okay. So we need now to talk about reaction, thermodynamics, and kinetics in a general sense. Your text takes you through a bunch of actual examples of reactions. And we'll deal with that. But to begin with, I just want to clarify what we mean by thermodynamics. This tells us why reactions happen. And the key issue here is in a process, do you form more stable bonds for reactions? Do you form more stable bonds than you break? And then for kinetics, the issue is how reactions happen. And this is an issue of mechanism. What does what? And we will use these curved arrows to show mechanistic steps. This is going to involve intermediates and transition states. And we've already dealt with intermediate/transition states when we were thinking about conformations of organic molecules. So we'll start with thermodynamics, and then we're going to move on to kinetics. For thermodynamics, the basic idea is that processes in our universe are favorable if they lead to a decrease in free energy. That's the Gibbs free energy delta G. And delta G, as you recall, is related to equilibrium constant. So for a process with an equilibrium constant KEQ, you can calculate delta G. If KEQ is greater than 1, delta G is negative. If KEQ is less than 1, delta G is positive. All right, that's sort of the fundamental relationship. If you want ln is natural log, don't worry about that. I'm not going to be having you calculate natural logs. And then if you wanted to calculate KEQ, that's the number e, or the exponential raised to the minus delta G over RT, so that you can see if delta G is negative, KEQ is greater than 1. If delta G is positive, KEQ is less than 1. If delta G is 0, then KEQ equals 1. So that's sort of the basic relationship to review. Is that sounding more or less familiar? Your eyes are sort of glazing over because this is reminding you of 105/106, and that was also a painful experience, so I'm sorry. I'm not going to be calculating stuff other than maybe adding, counting, and dividing by 2. So just, it's all right. As we talked about in Chapter 3 when we dealt with non-covalent interactions, this change in free energy has 2 basic contributions, delta H and T delta S. So delta H relates to, for a process, relates to bond strength for bonds formed versus bonds broken. And delta S refers to disorder. And with respect to reactions, delta S is usually pretty small, and we will almost always ignore it. But in general, just to be complete, I don't think these issues will necessarily come up in the future, but I want to sort of disclose times when you might want to worry about entropy. If in a reaction you go from 2 products to 1, that would be a loss of freedom / disorder. If you go from 1 product to 2, that would be an increase in disorder. Let's see, and if you have some molecule with 2 functional groups on either end and you do a reaction somehow that makes a new bond between them and you make a ring, that's going to lead to a decrease in disorder or entropy. It's difficult, so this is already too much that you didn't want to know. Entropy comes in units of kilocalories per mole per Kelvin. And so in order to determine how much entropy matters, you also have to know what the temperature is in Kelvin. So I'm never going to ask you to sort of offset and predict, well, this reaction would have been favorable, but entropy makes it unfavorable. We're not going to do that because you have to know not only what the entropy is, but what the temperature is, and that's just sort of too involved. We're not gonna deal with that. Okay. In general, delta H, we're going to make, because we're going to mostly ignore entropy, we're going to make the assumption that the change in free energy for a reaction is going to be related to, or pretty close to, the change in enthalpy for a reaction. And enthalpy is negative when the bonds you form are stronger than the bonds you break. All right, and it's positive if bonds formed are weaker than the bonds that you break. Sorry about penmanship there. Okay, so that's pretty straightforward, and that sort of makes sense in a process. If you make more stable bonds than you used to have, that's going downhill in free energy, so that ought to be favorable and spontaneous and so on. So the real question is, how do we develop some intuition for whether the bonds you form are more stable, more or less stable than the bonds that you broke? And the answer is just by practice. And for each reaction we discuss in this class, we're going to talk about whether it's thermodynamically favorable or not. We'll do so in general terms. We very rarely will actually do math. But here at the beginning, we're actually going to do a little bit of addition and subtraction just so you can see how the reasoning works. Okay, so we want to define organic chemists and physical chemists love tables of values that you can use and consult to go calculate new stuff. So it would be painful in terms of predictions to simply do every possible reaction and then write down the change in enthalpy for those reactions and then hope for the best, because that'd be too many things to do. Fortunately, delta H, you may have learned this, and this is not important, but I'm going to say it again, it is a state function. So delta H for a reaction, it does not matter for a process going from A to B. It does not matter how you get from A to B. Delta H for that process only depends on the initial state and the starting state. And what that means is we can take data from other reactions and use them to calculate the change in enthalpy for an entirely different reaction. So the reactions that scientists have done the experiments on and some of the calculations is on have been, sorry, coughing. The reactions that they've done these enthalpy measurements on are called bond dissociation. And, oh, we can't spell, huh? Bond dissociation. And we'll call this homolytic bond dissociation. This refers to a bond, say, between two hydrogen atoms breaking apart with an electron going back onto each hydrogen atom. By the way, this half-hooked arrow at the beginning, notice I didn't put another little flag there up at the top. The half-hooked arrow indicates the movement of one electron. So after this process, I have two hydrogen atoms, each with a single electron. This process is basically what would happen. Do you remember at the beginning of the class we talked about how you make a bond from hydrogens, two hydrogens, and you take the two 1s orbitals from hydrogen, you mix them together to get a sigma bonding orbital and a sigma star antibonding orbital. The bond dissociation energy or enthalpy is literally the amount of energy you'd have to supply in order to move one electron there and another electron there. Get them back from the bonding orbital back into the starting atomic orbitals. All right, so you've already thought about this, kind of thing. And naturally, breaking the bond should be uphill in energy, right? That's what a bond means, is you go downhill in energy to share electrons and to delocalize the electrons. So going backwards, that is breaking the bond, should be uphill in energy. So people measure the enthalpy for this process, and for, say, hydrogen, it's uphill by 105 kilocalories per mole. Remember, positive enthalpies are unfavorable, that's moving up in energy. Negative enthalpies are favorable, that's moving down in energy. So you would have to bring to the table 105 kilocalories per mole to break the hydrogen-hydrogen bond. Okay, and we can do this for all, this is called, because this delta H comes from a specific reaction, homolytic bond dissociation, we will actually call this a bond dissociation enthalpy. Or sometimes B, oops, that's not a B, bond dissociation enthalpy, BDE. Okay, so let's think about this for, dang it. Sorry, I'm trying to find a good example, but I will need to go somewhere else because the one in my notes I did not like. Okay, so sorry, I needed to find a reaction to talk about. So the reaction I'm going to show you is one that we'll get to in chapters 7 and 8. We're going to take this alkyl halide, T-butyl chloride, and we're going to add water. And what we're going to get is a substitution product where an OH group has been swapped out for a chloride group, and the other product we're going to get is HCl. So in this process, in order to sort of calculate the overall enthalpy for this process, what we need to know is the bond dissociation enthalpy for each of the bonds that we break / form. So I want to know what the bond dissociation enthalpy is for the carbon-chlorine bond. I want to know what the bond dissociation enthalpy is for the hydrogen-oxygen bond. Those are the two bonds I break, right? And then I want to know the bond dissociation enthalpy for an oxygen-carbon bond. And then I'm also going to want to know the bond dissociation enthalpy for the hydrogen-chlorine bond. Okay, and I can look these up in a table. I'm trying to figure out how much I care about kilocalories per mole versus kilojoules. Your text does math in kilojoules. I prefer kilocalories per mole just because of historical reasons, but I guess I can let go of that. I'm sorry. So 331 kilojoules per mole to break this bond. So this is the bond dissociation enthalpy. This is uphill. And then breaking the bond in water is actually uphill by almost 500 kilojoules per mole. The bonds that we form, the bond dissociation enthalpy for an oxygen-hydrogen bond is plus 401 kilojoules per mole. And then the bond dissociation enthalpy for the hydrogen-chlorine bond is plus 431 kilojoules per mole. Okay? Now, watch what we're going to do. Remember I said that because enthalpy is a state function, we can actually take these numbers from bond dissociation processes, and if we add and subtract them together such that we get out these molecules, it doesn't matter that these reactions didn't actually happen. We're going to get the same overall, we're going to get the correct overall value for enthalpy. Is that worth saying, or should we just make this simple? I think probably simple is better. So the overall enthalpy change for a reaction is going to be the bond dissociation enthalpies for bonds broken minus bond dissociation enthalpies for bonds formed. Why? Why do you think that's the case? Why am I subtracting the enthalpies for the bonds formed? Yeah?
When a bond is formed, that energy is released.
Right. When a bond's formed, that energy is released. Forming a bond would be the backwards reaction, going from these two to this product. So I'm going to add these numbers up, 829 kilojoules per mole. I'm going to add these numbers up, 832 kilojoules per mole. Bond dissociation for bonds broken, 829 minus 832 kilojoules per mole. Overall, I would estimate that delta H is minus 3 kilojoules per mole. That's really small. If you did the math, the equilibrium constant would be really close to 1. And you'd basically have a 50-50 mixture of products and starting materials. Remember how I said about 1.4 kilocalories per mole, at room temperature, about 1.4 kilocalories per mole is equal to equilibrium constant of 10. So, and there are 4.184 kilojoules per kilocalorie. So anyway, you can see that this is much, much less in energy than the amount that would be consistent with a factor of 10, so you can basically say it's sort of a one-to-one mixture. All of this isn't so important, I'm just putting this number in context. I don't want you to look at that and say, whoa, that's a huge number, because relative to the energies of the bonds you formed, that's almost nothing, right? Okay. All right, so you can estimate whether a reaction will be favorable or not based on that.
So would the reaction be favorable?
You would expect it to be, would it be favorable? Well, you'd expect it to be basically in equilibrium with the equilibrium constant close to 1. Okay, so if you go in the lab to do this, you expect probably not that high yield. You expect it to run until it's about halfway done and then stop, which seems like a terrible thing. And so you might have to do something to isolate your desired product from your starting materials. And that's where we start bringing in practical strategies. You learned about Le Chatelier's principle, which is that if you do something to increase this rate of reaction, say increase the concentration of one starting material, equilibrium will shift towards the products, or if you do something to reduce the reverse rate of reaction, if you remove one of the products, equilibrium will also help favor the products. And so we can do those kinds of strategies to take a reaction that's kind of cruddy in terms of equilibrium constant and move it to completion. And you'll encounter those kinds of strategies, specifically if you take the Chemistry Lab 353. Just another quick example of this kind of thing. Do I dare? Why not? But it's going to depend on me looking up the right values in a table, which is boring. Let's do another reaction. So this is an elimination reaction. We're going to take an alkoxide nucleophile / base, and it's going to remove a proton from this carbon, and we're going to get as a product a new carbon-carbon pi bond. We're going to get a new oxygen-hydrogen bond, and we're going to get Br minus. This happens to be an elimination reaction because you're eliminating both the hydrogen and the bromine from the starting molecule. Mechanism isn't important yet. We won't talk about it. If we think about, we won't talk about it yet. We will in chapters 7 and 8. If you think about bonds that we break in this process, we break a carbon-hydrogen sigma bond. We break a carbon-bromine sigma bond. And then bonds that we make, is a carbon-carbon pi bond, an oxygen-hydrogen sigma bond. So we can sort of look up those bond dissociation enthalpies. I'm going to try to find the table and get numbers that are as close as possible to what we might be dealing with. Okay, the carbon-hydrogen bond here should be about, looking at the table, about 95 kilocalories per mole. The carbon-bromine bond should be worth about 285 kilocalories per mole. The carbon-carbon pi bond, the table often doesn't list that, so you sort of have to do math from with some other numbers. I've calculated it before though, so I'm gonna, nope, actually I didn't. Dang. Okay, stay tuned on that carbon-carbon pi bond. An oxygen-hydrogen bond should be worth 119 kilocalories per mole. And then the carbon-hydrogen pi bond is, I'm going to make up a number which is close to right because it's not in the table that I'm looking at. If you needed these numbers, I would give them to you in a table on the exam. You're not going to be memorizing anything. Carbon pi bond is worth about 68 kilocalories per mole. It's weaker than a sigma bond. So we would add these up, but I'm not good at arithmetic on the fly. So there we go. 380 kilocalories for the bonds that we break. And then 187 for the bonds that we form. Did we get all the bonds that we formed? I think so. Yeah? Okay. So overall, if you were to calculate the change in enthalpy for this reaction, you would say bonds made are weaker than bonds formed. And so you might be tempted to conclude that this was unfavorable. There's a problem here, though. If you go back and look at these bond dissociation enthalpies, they all come from processes that involve neutral radicals. Okay? And if you look at our products here, we have a negatively charged starting material and a negatively charged product. So it's possible that we haven't accounted. This math that deals with the strength of the bonds formed versus broken does not deal with, we haven't accounted for the difference in stability of a Br minus versus a negatively charged oxygen. Okay? So how do you know which is more stable, Br minus or the negatively charged oxygen? So Br minus, you're right, is more stable, but you know that because its conjugate acid, HBr, has a pKa of -9, whereas the conjugate acid of the alkoxide, has a pKa. In this case, for this particular alcohol, it's closer to 19, but 16 would have been fine. So actually, in terms of equilibrium constant, you're looking at 20, how many orders of magnitude? Something like 28 orders of magnitude in terms of stability difference between this negatively charged alkoxide and this bromide. And so that's enough to overwhelm the fact that in terms of bond stabilities, this is uphill. So if we take 380 minus 187, we would be tempted to conclude that delta H is like plus 193 kilocalories per mole. But we haven't accounted for the difference in stability of the alkoxide versus the bromide, and that's such a huge difference. And if we wanted to, we could do the math and figure out what this equilibrium constant would be, and then we could compare that to the difference in pKa, and we could come up with some conclusion. I'll just tell you what the conclusion is, and that this reaction's favorable in the forward direction with basically 100% yield. Okay. So the numbers aren't as important as the process, and even that's not as important as realizing that processes are favored if you make more stable bonds than you break. Why do we care? Why are we talking about this in the first place? I feel like it's important to dispel a possible misconception that I think some of you may come out of biology with. And that has to do with, let's see, where is it? No? Okay. That has to do with ATP. Some of you have likely been told before that the breaking of a bond in ATP releases energy. Does that sound vaguely familiar? Ish, yeah. As an example, I'll show you a reaction from glycolysis. This is the molecule glucose, beta-D-glucopyranose. You won't have to deal with that until 352. And this is the horrendous molecule ATP, which I am going to draw for you in completeness, but you don't need to memorize it. Oh, I love ATP. It keeps us all alive, right? But it just is maybe painful to draw. All right, that's the adenine base. This is the ribose sugar, and then you need the triphosphate portion. And you may have even been taught that these phosphorus-oxygen bonds are relatively weak. So this is ATP. And in this process, there's an enzyme called hexokinase that transfers a phosphorus group from the end of the ATP molecule and puts it on the terminal or the carbon-6 hydroxyl group of glucose. And then what you have left is not ATP, but you now have ADP left in its place. And this is strongly downhill in energy. I forget by how much. So I'm making up a number, which I shouldn't do, but all right, I will hedge. It's strongly negative, meaning this is way downhill. Okay? Now, some people are tempted to say, oh, the reason it's way downhill is because we broke a bond in ATP. And that's categorically false. Breaking bonds always takes energy. All right? And you can see that from our bond dissociation enthalpy stuff and from the stuff we talked about at the very beginning. You want to break this bond between hydrogens, you've got to put in energy. You want to break a bond between carbon and chlorine, you have to put in energy. Even for this bond that's between the phosphorus and the oxygen, the one that we break is right here. Even that bond you have to put in energy to break. Okay, so then you've heard ATP is the molecule that carries energy around your body. How does this work? And the answer has to do with the stability of the bonds you form in a process versus the bonds that you broke. So the bond that replaces the one that we broke in ATP is this oxygen-phosphorus bond. This kind of bond is called a phosphoester, and this kind of bond over here is called a phosphoanhydride. That's not important right now, but I will tell you that the phosphoester bond is stronger than the phosphoanhydride bond, and that's what drives this reaction forward. Okay, the fact that we make a stronger bond than we break. Does that make sense? Stronger bonds, yes, release. The energy released when you form stronger bonds more than compensates for the energy absorbed when you break the weaker ones. Okay, and this is true for ATP hydrolysis as well. We could take this ATP molecule and we could say add water, and we would get out afterwards ADP plus phosphoric acid. And people say, oh, this is downhill in energy. And it is, but the reason it's downhill in energy is because the bonds that you form are more stable than the bonds that you break. All right, so that's a minor point because frankly, what they didn't tell you, what you may not have appreciated in biology is just that we very rarely do a process where bonds just break. We often also do, coupled with that, are bond forming processes. So probably when they told you breaking the bond in ATP releases energy, what they meant was that the stuff you make is more stable than the stuff you broke. But it's an important distinction, all right? The energy that's released in this process is released as heat. So this is one of the reasons why our body's temperature is about 98 degrees Fahrenheit, is because we've got these processes going on inside of us, 37C. In some cases, you can couple in many cases, you can couple the downhillness of one process with the uphillness of another. And we can leave the rest of that for a biochemistry class. So we'll pause there. Go ahead.
This is a curious question. So you said our body is heated up to 37 degrees Celsius normal body temperature. When we get sick and our body heats up, does that mean there's just a bunch of favorable chemical reactions happening to heat us up?
That's a good question. When your body heats up, is there a bunch of favorable chemical reactions making that happen? I don't actually know the answer to that in a lot of detail. What I will say is that fever is associated with an inflammatory response and an immune response. And so I don't know why you would want elevated body temperature, but presumably those processes make it happen. Also, the fact that our body temperature is what it is and it's held pretty constant is related not only to those processes happening, but also cooling processes. And so another way you could heat up is if your cooling processes aren't as efficient. So yes and no, and I don't know. Any other questions you want to ask about stuff I don't know? Okay, well, let's take a couple minutes. We'll come back and talk about reaction kinetics.